In this section, we focus on principles of model building, verification, and validation. These are conceptual foundations that helps us understand if a simulation model can be trusted. So let's start with the purpose of validation. The goal is not to create the perfect model, but to create a model that represents the real system well enough for a decision making. Validation helps us increase the model credibility to an acceptable level. A model can be considered credible when users approve it and when it is actually used to support real decisions. And this is really very important. Validation is not about proving that the model is true. It's about showing that the model is useful for specific purpose. So a credible simulation model is one that stakeholders trust to provide results that are accurate, consistent, and relevant for a decision making. The following slide shows the relationship between the real system, the conceptual model, and the simulation model. We always start from the real system. First, we observe how the system actually works. We identify interactions between components and we collect data about its behavior. Based on this, we build the conceptual model. This is where we define the structure of the system, make assumptions, and decide what data we need and how we will collect it. After that, we implement the model in a software. This becomes the simulation program or simulation model, or sometimes in the literature you could find out the title operational model. The important part here is that verification, validation, and calibrations are not isolated steps. They connect all levels together. We validate the conceptual model against reality. We verify that the implemented model correctly represents the conceptual model, and finally we calibrate the model using the real data. So this one is iterative process, not a linear one. The following slides demonstrates the formal definitions of verification, validation, and calibration. Verification means checking that the model is implemented correctly in the software. Validation means checking if the model behaves in a similar way to the real system. Calibration is the process of adjusting model parameters so that the model outputs better match real data. In practice, these three activities are closely connected. So my experience shows that usually students are mixing verification and validation. Therefore, I have created the following very narrow but quite clear table which compares verification and validation. As you're able to recognize, there are several aspects which are demonstrated in frame of the table. So what is let's say, a difference in a purpose for which one we are utilizing verification and validation? What is the key question we are asking in frame of verification and validation? What we are focusing on, what kind of techniques we are utilizing, and what is expected as the outcome from verification and validation. Also here I would like to note that the last two rows actually are not directly related with verification and validation, but they're really very important. The last row, timing, actually shows us or give impression what is the timeline when we are applying verification and validation, while an aspect performed by indicates who is in charge of completing verification and validation. So to be honest, when we are talking about verification, it shall be stated that right now the role of verification is a bit cloudy. Why I am providing you with the following statement? Because right now the modern simulation software is really, I would say, really user-friendly, meaning that a lot of the things we could control, and by this one we are making much more less technical mistakes implementing the model. But still, the following slides gives you an impression what kind of verification techniques we are able to utilize. And the first one implements, sorry, not implements, of course, but states that we are able to use a very simple approach which can be called a peer review, meaning that we could provide the conceptual model and developed simulation model to some third party, now a person, just to review and check if it's working correctly. The second one is based on, let's say, drafting or drawing the diagrams which demonstrates different logical paths inside the model, and this one is really very useful to catch up if the model was implemented correctly. This one is really very useful when the model is complex and there are really a lot of different pathways. So the next one actually is talking about testing the model outputs, exploring if following outputs are realistic or unrealistic. The next one is regarding printing and outputting the parameters, which can be useful to check up that we have provided the correct parameters. A very important aspect, and here I would like to pay your attention because in my opinion this one is a really very practical advice, I would say, is the following: make the model self-documenting. So meaning that most of the software, I mean simulation software, provides you an ability to customize the title of blocks or specific elements inside the model. Please do not ignore the following opportunity. So meaning that it's much more easier to understand what is happening inside the model if you are providing meaningful names for the blocks. So instead of, I don't know, activity 1, activity 2, activity 3, activity 5, you could give a self-explaining names like unloading process, quality process, loading process, printing process, and so on. Of course, animation is really very powerful one, which allows us to check if all the workflows were implemented in a correct way, if all the paths are working, and so on. And of course, the last one is a graphical representation of the model. Here, different techniques can be used, but in any case. A graphical representation allows us to see the dynamics of the system and evaluate if the following dynamics corresponds to overall understanding of how system operates. So here we see validation and calibration as an iterative process. Validation means comparing the model behavior with a real system. A calibration means adjusting the input parameters to improve the match. On the right, the diagram shows how we are repeatedly compare, revise, and improve the model. We can compare the model in two ways or using two different approaches or techniques. One is based on subjective testing, and here we are involving experts for completing the judgments, while the second approach is based on objective testing or objective tests. And in frame of this second approach, we are comparing the real data and the model output. A quote reminds us that models are never perfect. What really matters is if a model is useful. So the goal of validation is not perfection, but practical usefulness for decision making. So a following slide just sum up all the ideas which we have discussed. I believe all the bullet points which are represented here are clear and just show you the essence of our discussion. So please maybe press the stop, try to go through the bullet points and catch up if you are understanding in a correct way all the concepts which are described here.